All right, so I want to do a quick video showing you how to go through the notes that are up for beginning of vectors. We talk about vectors. What vectors allow you to do is perform, what we're going to do here is perform operations with geometrically defined vectors. They're going to be given as just basically an arrow. Why? Well, one main reason is vectors are used heavily in understanding the effect of forces in physics. So whenever you look at how things move, how forces interact with things, vectors are everything about how we understand that. I mean, it's like everything we do is based on vectors with that. Okay. So anyway, to start out, a vector consists of a magnitude and a direction. It can represent various concepts such as forces acting on an object or traveling a certain distance in a certain direction. If you ever watched Despicable Me, whenever the character Vector comes out, he actually kind of gives a good definition of what a vector is when he introduces himself. Anyway, geometric representation. In that case, length represents the magnitude or how strong it is. That could represent things like how fast something's traveling, the amount of force or velocity it has. Direction represents, really all I can say there is it's the direction it's headed, direction it's moving. That's all there is to that. It just, like, this means it's headed that direction. Now, when you have a geometric representation, you can have just arrows, and we can do all of our stuff that we're going to do with arrows. Now, when you get a little more detailed with it, you might have an arrow that has a specific angle direction and a magnitude with it, and be able to measure things and be very exact with it. But, you know, that's just one aspect of it. Now, to give you some other forms for vectors, you can have algebraically defined vectors with a horizontal component and a vertical component. You can have it given as an actual point, and what that means is basically from the origin to that point. So if you had the vector 2, 3, or 2, 3 in these vector parentheses, the sharp ones, that would mean you go 2 up 3, here it is, and your arrow would go from the origin to there, unless it otherwise specifies that it starts at one point, ends at another. Another way it could be given, that same vector could be 2i plus 3j. Now this is not the I complex number I. This is what's called a unit vector in a certain direction. So like if I see I, the I vector is the vector 1, 0. So it's 1 unit that way. And the j vector is 1 unit vertically. And so that would mean you have 2 I vectors and 3 j vectors, and you end up at the same point for what that ends up being. That's used a lot more for 3-dimensional vectors when you get into that. It can be used for 2-dimensional vectors, though. For 3D vectors, it's I, j, and k. K being a z third-dimensional 1-unit vector. Polar. So it has a magnitude component and a direction component, r and theta, just like all the stuff we've been doing with polar coordinates so far. There's a big connection between polar coordinates and vectors. Honestly, when you get into physics, you're probably going to see a lot more stuff that's in a polar type form than it is in an algebraically defined form or a geometric representation. So what that's going to do is, the way we're going to see it, we're going to see r and theta. But in an actual physics class, a lot of times, now you can translate it over to something like this, and I honestly kind of think this is a little easier to work with, but they'll say you have a force of 20 newtons in a direction that is 20 degrees north of east, okay? And that just tells you that your direction you're going, think of east north, west, south. 20 degrees north of that is, if we're in polar coordinates, that just means our polar part of it, our direction part of that is 20 degrees. That's a lot easier to write than that, but in physics, they tend to do that. And then our magnitude part would be 20 also, because that's the force, okay? Now, the main one we're focusing on in this set of notes is this one right here, okay? Geometric representation. It's how we can get a quick sketch of a combination of vectors and see what's called a resultant vector. The resultant vector is when you put them all together, put all those forces going various directions together, what they create, the resulting force, okay? Now, I also always like to point this out. Whenever I was, the first few years I was teaching pre-calculus and included all this, I remember we had an online computer-based test, and we hadn't done vectors at all. And the very first question was something like this plus this. And like, I saw students who like were really good students and worked really hard all year long look at me like, what have we done? And so I've made my adjustments and you know, kind of changed the curriculum around some. But here, in adding those, I'm going to show you how to do that here in just a second. But it's really not a long or difficult process. Okay. So how do we add vectors geometrically? First way is with parallelogram method. Okay. You draw a parallelogram with the vectors as sides. So whatever this vector is, you have an origin point up, and then you draw the other vector from it. And then a parallelogram, if you recall, has parallel sides. So this should be parallel to this. This should be parallel to this. And the resultant vector goes from the point you started at to the opposite vertex. So the diagonal is the result, and that's called the resultant. Okay. So good intro. We're going to get those other pages in here, and that's all we've got for today. Now, next part. So if we have to do resultant vectors with these, and what I want to encourage you to do is watch me do the first one, and then try out those other three and compare and make sure you make whatever adjustments you need. Okay, so we're going to do vector A plus vector B. Sometimes you'll see this little vector symbol above the letters. Other times it'll just be a bold letter when you're dealing with vectors. You can see several different notations, but they're all vectors. So we're going to pick a starting point, and you want to make sure that it's going to have enough room to get the full parallelogram in there. So if you notice, this one goes down, this one goes up. I'm going to put it right here so that I can draw the down one. And if you notice, I didn't do a very good job being exact with that. So you do have to be a little careful. Don't get too off with them. These are just general sketches, okay? This is not something that I can look at and be like, oh, you're 2 degrees off, you're wrong. That's not how this is going to work when we're doing sketches. Now, if we had more exact numbers, then yeah, we'd want to be more exact. But here, we're just putting vectors together, getting the basic concepts of how they add. All right, so what we're going to do is draw those initial 2 vectors. We're going to draw parallel sides with dotted lines. And we're going to go from the point we started at to the opposite vertex. And this is our resultant vector right there. Okay? That's our resultant vector. Simple as that for parallelogram method. Parallelogram method is better for when you have just 2 vectors. The second method is probably better when you have 3 or more. You can do 3 or more vectors with the parallelogram method, but I don't like to do it that way because it ends up with more than one problem to do a single problem. Well, let's put B and D together. Notice this is up and way right, so make sure we have room. There's our up vector with our starting point. We're going to do our, let's see, not quite long enough. Let's make it a little longer. Let's see. There. That's close. Again, we're not being super exact. Like I mentioned before, pause it for a minute and try them and then compare. parallel, parallel, starting point to opposite vertex. That's our resultant. And if we actually had forces that were modeled by that length being proportional to, say, the mass, the force, the velocity, and we combine them together, the resultant would be equivalent to that. It's kind of like, if you think about it, if I walk straight north for 3 miles, and then I walk straight east for 3 miles, what would be the equivalent to get me from the starting point to the ending point? That's kind of how this is working, okay? And that'd be like 3 times the square root of 2. You could do the trigonometry with it if you wanted. We'll get to that later. All right, so C plus A. Let's see, I'm gonna start up here. There's our A vector. It doesn't matter the order you draw them in, you should end up at the same result. There's C, there's A, pretty good. And here's C, pretty good. Parallel, parallel, beginning, opposite corner. There's my resultant. I'm gonna label these just so we have them. That was vector A and vector B. This was vector D and B, and this was vector A and C. Next one, A plus D. Let's see, we gotta have room here, so I'm gonna start here. I'm gonna go down for A, and then from the same vertex, try to get as close as we can, and then we're gonna go parallel with it, parallel with it, and then from original point to the opposite vertex. This was D, this was A, and there we go. Okay, now, second method is tip-to-tail method. I prefer this. It's hard to get with this diagram right here and know exactly what's happening there, okay? So just make sure, again, like follow along with the first example with it, try them yourself, and compare with what's on the video. So tip-to-tail method is we're gonna pick a starting point and we're gonna literally go tip-to-tail. The tip of the vector gets attached to the tail of the next vector. So to get this, A plus B, let's see, we're gonna do, so we're gonna pick a starting point and we have A and B we're gonna put together. So we're gonna draw our A vector, and from its tip, we're going to attach the tail of the other vector. We're gonna go up, and we should get, now again, these are not gonna be exact because my vectors are not perfect here, but we should actually get the same vector we got. This was A, this was B, and there's our other vector. And you notice, because I was a little bit off on one of these, that this one's pointing down a little bit more. Let's see if we're a little closer on the next one. Good pausing point. So right here, we're gonna sketch first our B vector. Looks about like that. And then from its tip, we're gonna draw the tail of the next vector. And then we're gonna go from the starting point to the tip of the last vector. Make sure you do that. You're gonna start at your starting point, end at the tip of your last vector. That one looks a lot closer to that. And those vectors are equal. Even though they're in different locations, they're equal. If they have the same direction, same magnitude, pointing the same way, the same length, they are equal. That's the rule with vectors. So let's try C and A. C goes down like that. Maybe didn't do the best job drawing that one. And then A kind of goes down like that. And our resultant goes from the beginning to the tip of the last vector. There we go. Last one, A plus D. We're gonna do the same thing. Pick a starting point. I'm gonna go, here's my A vector. Again, I didn't do the best job preserving the direction of that A vector. And then from its tip, draw the D vector, go from beginning to the tip of the last vector, and that's your resultant. All right, now we have scalar multiples. We had scalar multiples back in matrices. And in fact, the things that you do with matrices are very closely tied to what you do with vectors. Actually, any vector can be considered a matrix, and then various matrix operations then apply to it. We don't have to look at these as matrices. We can kind of look at them as their own thing, but there is, if you ever take a class called linear algebra, you deal with a lot of stuff with matrices, and when you do that, you have concepts called vector spaces and things like that, because honestly, a matrix and a vector are really kind of interchangeable ideas. So if we see 2a, we're going to take the a values from up here, way up there. Okay, 2a, we're going to start at a starting point, and we're just going to actually draw 2 a's on end like that. Your resultant goes from your first point you started at all the way to the end of the second one. When you do a scalar multiple on a vector, it doesn't change the direction, it just changes the length of it. If we see 3 b's, this is a good pausing point to check yourself if you want. We're going to sketch 1b, 2b, 3b. Resultant goes from the beginning to the end. And if you wanted to redraw that, that might be a good idea too. 3b would look like that. 2a would look like that. Negative d, if we have negative scalar multiples are going to be the opposite direction. That's what's going to happen. It's going to flip the direction. So instead of going to the right, it's going to go to the left. Okay. If it's going down and to the right, it's going to go up and to the left. So instead of pointing to the right, this is just going to point to the left and go the same distance. So there's negative d right there. Negative 2c. We're going to pick a starting point and we're going to draw 2 opposite direction c vectors. So c, just for reference, this is not getting the actual result here. C looked kind of like that. So we're going to draw 2 of those go in the opposite direction. Here and here. Resultant vector goes from the beginning point to the end. So if we wanted to redraw it for more accuracy, that would be negative 2c as a vector. Last page. So we put all that together. We're going to reference the same vectors we had before. We're going to use tip to tail on this, okay? When we do that, here's how it's going to work. If we have a positive version of the vector, it goes exactly like it was before. If it's a negative version of the vector, it goes the opposite direction. Like this negative c is going to go the opposite direction of c. Instead of going down to the right, it's going to go up and to the left. It's like you flip the tip to the other end. And then you combine them as necessary. If I do a plus 2b, we're going to put our a vector. We're going to put 2b vectors. Those are the little ones that went up like this. And your resultant is going to go from the beginning point to the tip of the last vector, just like that. Next one, 3a minus c. We're going to do 3 a's together first. So 3 a's, 1, 2, 3. And if we have a minus c, instead of going down and to the right, it's going to go up and to the left. And then you go from your beginning to the tip of the last vector you have, and that's your resultant. Okay. If you haven't paused already to try them out yourself, that would be a good point to do it right now. All right, so next one, 4b minus 3c. So we got 4b. We're going to start 4b, 3, 4, and then after that, 4b minus 3c. So instead of, oh gosh, I put myself in a bad place for this one. Let's see how it works. Instead of down and to the right, it's going to go up and to the left. We're going to do 3 of those, like that, like that, like that. Beginning point to the, it's going to be tough to get all the way there with a straight line. That's our resultant vector right there. Last one, we want 2a minus 2d. So we're going to start out, realize we're going to be, instead of going to the right for our d, we're going to go left for the d vector. So we're going to start, we need room this way. So 2a's, And then minus 2d is going to point us this direction with 2. And the d vector was like that. And so we're going to go from our starting point to the tip of the arrow of our last vector. There it is. And that's how we add and subtract vectors geometrically. Okay. So other notes to consider here. To be considered equal, vectors must have the same magnitude and direction. It doesn't matter where they are. It just matters even if you had a bunch of vectors drawn in space. If you had that vector and they were the exact same direction, exact same magnitude, they would be equal. Also, the magnitude of a vector is often symbolized with absolute value. So absolute value. Sometimes it'll be a double absolute value. Okay, so that is all for your notes.